Today, we're going to learn how to make this very cool shader effect. It doesn't use any custom 3D modeling. In fact, it uses the basic Three.js sphere, a vertex shader, and a fragment shader. So let's get started. I've set up the scene as a very simple React 3 fiber scene. We've got the canvas, we've got a black background, we have some orbit controls, and of course, our sphere. So I've split the sphere into its own component. And within that, you've got mesh, there's icosahedron geometry, and a custom shader material. These vertex shaders and fragment shaders are defined like so. They are the world's simplest vertex shaders and the world's simplest fragment shader. This tutorial is very much inspired by Wael Yasmina's tutorial on how to make this animated blob using a vertex shader. Some of the contents have been taken from this, so definitely go check out his channel. And thank you, Wael, for sharing your insights with us. Firstly, we're going to learn how to perturb the vertices on the sphere. And to do that, we're going to use perlin noise. So let's go to this repository here, which is github.com, Ashima WebGL noise, go to source, and then we're going to copy the classic noise 3D GLSL. We can copy that straight into our vertex shader above the main. Now we can make use of the perlin noise function. So that would go like noise. We can sample the noise at a position. So we're going to use the vertex position itself and then define the repetitions. For this, I'm going to define the repetitions as 10. Now we can use that noise to extrude the vertices along their normals. So the normals are the way that their faces, those triangles, are facing. What I'm going to do is define a new position, which takes the old position and simply adds noise, the normal times noise. And then rather than return position, which is taken from the mesh attributes, we're going to return this new noise, this new position. So as you can see here, the sphere is being stretched and pulled in the direction that it's facing. We can reduce that slightly by applying a scalar quantity to noise itself. So we've got something that looks a bit more like the target that we're looking for. So this is very cool, but it's quite static, and the target that we had, visual target, was all moving around. And if we notice here inside position, we can sort of offset it slightly. So if I keep going like so, you can see the thing move, and then yeah, it's starting to come alive. Now, obviously, we can't just keep incrementing that. At some point, we're going to have to ship this code. So one thing we can use that increments upwards, one thing I can think of is time. So if I go to 3 canvas, I want to pass in time, which increments, and then I can use that as the thing that I'm adding onto the noise sampler. So in order to do that, we're going to introduce a concept known as uniforms. And uniforms are simply ways we can pass information to a shader. Firstly, I'm going to define inside our shader material argers a new parameter called uniforms. And then within that, I can define something called uTime. Now, u underscore is just a sort of convention to denote that this variable is actually a uniform, and uniforms are simply shader talk for constants, so they're constants across all shader threads. Right, and it expects an object to be passed like so. So I'm going to pass in, for now, a value of 0.1, just to show that we can access the variable. And the way we access the variable is inside our shader. We can then define a keyword using uniform, its type, which is a float, and then the name of the uniform itself. And it's just as easy as that. Now, when I plug this in here and then increment this, we should see that time is, what have I done? Sorry, that is the wrong place to put it. uTime. Now, we can see that is kind of doing some motion here, and I want to increment that using the built-in time variable inside Three.js. So I'm going to do this I'm going to define a time. So I'm going to define uTime like this, and then use ref. I'll use ref so that the object doesn't change between re-renders. I think we need a little import. So command period add import. And then I'll use a React 3 fiber hook known that's called useFrame. So useFrame essentially re-renders the component every frame. And we also get some information here. One being the state. I'll give it underscore because I'm not using that state. But what I'm interested in is delta. And delta is the time between frames. So when you think of frame rate, 30 frames per second, 60 frames per second, how much time has passed in between those frames. And I'm simply going to do this. u.current. This is kind of React world now, .current. And then value. And simply keep adding delta to uTime. And that has just been passed like so. And I'm going to call it u.current. And there we have it. This is now animating over time. Super cool. Our next thing to do is to apply a different effect where the mouse is hovering. So currently you can't really see any hover effects. And to do that, we need to raycast onto our sphere to figure out where in the world the position that my pointer currently is. And this is how we do it. We are going to use we're going to access a few things from Three.js. So we're going to access the camera. We're going to access the pointer. We're going to access the raycaster. I think that's all we need from use3. And inside here, and I think we also need the scene. Then inside here, we're going to do the actual raycasting. So raycasting is essentially shooting a ray. We're going to shoot the ray from the origin of the camera, so where you are, and into the scene, and then tell us if we hit anything. Raycaster.set from camera, and we're going to take pointer, and then pass in the camera that we're actually using. Then we need to check if there's any intersections equals raycaster that intersects object. And then we're going to use the scene object and recursive. Yeah, why not? Then we need to check if there's anything that actually intersects. So if I console.log intersects right now in this console, you can see it's not currently intersecting. But then when I do intersect, something's happening. So we've got empty array. Now I've got something inside the array. Let's just scroll in and see what we've got there. And this is telling us the object that we've intersected with. So we can do some simple check that says if intersects the length is more than 0, we've got something. And inside here, we want to grab that position. So we want to store that position somewhere as well. And we do that. And when you think storing things, think of either state or ref in a React world. I'm going to use a ref. Again, I'm going to kind of do this object here. And then, so an initial position of the mouse is, we're not going to want it anywhere near this. So we're going to just say new vector 3, say 0 on the X, 0 on the Y, and then let's say -5. So it's nearer the camera. And then when that intersects, we can actually set it to intersects 0 dot position dot point. And now we can pass in that position to the shader, again using uniforms. And then finally, like before, we can define the uniform inside the shader. This time its type will be vec3 because we're dealing with vector 3s. So now we've got the mouse position inside the shader. We need to kind of visualize that something is happening there. And one way we can do that is to say any vertices near that mouse position do something special, and when they're far away, you kind of don't do anything. So we got this kind of like hover effect. And the way we actually do that is we have to figure out the kind of hover area. Let's just call this hover area. And using the concept of the distance, what we can do is say that, because when we're dealing with vertex shaders, we're dealing with a per vertex. It's like a per vertex shader. So we know the position of this current position of vertex, but not its neighboring one. So this is kind of the way we have to do that. It'll be a bit clearer once I've done it. We're going to grab the distance, which gives me a distance between 2 points. We're going to first get the distance of the mouse position, then the distance of the position of the vertex position itself. Now I want to figure a way to visualize what that looks like. So what I can do is pass that value, hover area, to my fragment shader. And the way we do that is using another P word called varying. And varying simply says pass from the current shader onto the next shader in the pipeline. I'm going to do a V hover area, like so. And then rather than kind of define that as a float, we're going to reuse that. Oh, sorry, this should be a float. And then inside the fragment shader, I can copy this line like so. Replace our color, which is currently white, with a single. We can do this. So the RGB values, we can see here that it's darker where the mouse pointer is. That's because the distance is 0. And when we're doing fragment shaders, 0 is black, and anything and white, 1 is white. So, and it kind of gets truncated to that. So things near the mouse cursor, the distance is 0, but things further away, the distance is nearer to 1, kind of, and above. Kind of, this area is fairly large. We can reduce that area by getting that V hover area and dividing it by some radius. So let's say 0.4. We now can see that it's very subtle. Maybe I can, yeah, it's a bit subtle. So let's just stop it for a minute and figure out why this works. If you take a number, we got V hover area, which is a number that's going to go from 0 to 100, maybe even infinity, depending how far those objects are from the mouse. If you imagine a sliding scale, so if you do 0 divided by 0.4, you're still going to get 0. You do 0.2 divided by 0.4, you're going to get a half. And then the closer you get to 0.4, the closer you get to 1. And then as you get past 0.4, then things are going to be above 1. So for example, 0.4 divided by 0.4 is going to be 1. 0.5 divided by 0.4, now you've got a top-heavy fraction, so that's going to be above 1. So actually, what we're seeing here is not, the white is not 1, it's actually everything above 1. So we want to clamp that down, actually, so that the values are always between 0 and 1. So we can use a function called clamp, and we're going to we can clamp this number between 0 and 1. Now the effect is going to be the same, but what we don't see is that, because 1 gets kind of clamped, and then once we have everything between 0 and 1, we can invert it. Equals 1 minus V hover area. And now this becomes a bit more apparent what we're doing. And now we can see that kind of like that glowy hover effect. I can even increase this a bit. Maybe even do something like that. We could, yeah, and now we've got a pretty nice glowing effect. So we now know that anything, this value here per vertex, if it's more than 0, you're inside the hover area, and if it's 0, then we're outside the hover area. And so using that, we can do some really, really cool things. Um, it's, it's probably not fair to call this a v-hover area. That might be a bit confusing because we are looking at per vertex. But we're just saying that what is your value according to the mouse position and your vertex. So we're asking that vertex, how far are you from the mouse? So when it's there, it's like 0, and then we invert it becomes 1. When the mouse is over here, that same vertex has now become so far, it's now 0. Now, what we'd like to do is to show 2 different colors based on where you're hovering. And rather than select individual RGB, I'm going to use a function, I'm going to use HSL, so hue, saturation, luminance, because it's a bit more intuitive to me, and we can do some kind of easier transitions. We can use time to kind of slowly move between different hues. I'm going to grab my HSL to RGB function from this link here. So thank you very much to Anastandumba for your function. Copy it straight into my fragment shader. And you can see that what this is doing is I can now work with hue, saturation, and luminance. I'm going to say something, I'm going to find a base color. Let's just call it give it effect 3. So for hue, let's just say 0.2, saturation 0.5, and luminance maybe something a bit lower. Let's see what that looks like. Okay, very nice. And then for the hover color, I'm going to use the same base color, but just increase the luminance. So you can see what I'm doing here. Right, simple stuff. And then I don't need color anymore, but I can replace it with a mix between the 2, base color and hover color. And then use that hover area, that value that goes from 0 to 1. So this mix is telling me when this value here is 0, let's just to prove the point, is going to be closer to X or the A. And then when this is halfway, we're going to mix in between. Then when it's fully at 1, it'll be hover color. And so I don't know if you know what I'm getting out of this is that, okay, with the mix, we can start to do some cool hovering effects because we're mixing between the 2 colors now. That is very nice. And I can even let's just remember that time uniform I sent earlier. Well, I can access that from this vertex shader too. And why don't we use time as our hue? And now we're going crazy disco, but we can sort of like slow that down a bit. So let's say time scaled. Let's scale it down to 0.2 and replace these 2 times with something a bit slower, a bit more gentle. Yeah. And then let's maybe just reduce the saturation on that a little bit, increase it on this a bit. And now we got our hover effect, and it's like cool. The background color is changing, and yeah, I don't know. I'm excited. This is just a simple sphere, and under 30 lines of code. If you exclude all the stuff we included, like 30 lines of custom code, we're already getting this very cool thing that's like not possible with 3D modeling, or might be very difficult, but like the GPU is so powerful once you get to know how to do it. Now, okay, that's the hover effect done. And there's a few things I kind of want to do. Like it's still quite static. There's another thing we can do using that hover area to drive the effect is that, so we've got this kind of noise. We've only used one noise, but you can layer the noises, right? You can have multiple noises. I'm going to move this bit down here because I'm going to use the hover area. No, go away. Yeah, so we're going to have, and then what if we do noise, hover, and it's the same effect from before, mixing between the two. What if we do that with noise? So like position plus U time, and then using the same kind of sample, the repetition. And then, do you remember this thing here where we scale down the noise? Let's move that over here. Right. But this one, let's not scale it down. Let's just keep it at 1. And then, so noise hover. Let's just see. Like, this is going crazy. All right, that's a bit too crazy there. Maybe that to 3. Yeah. And then let's mix between the two. All right, noise mixed. And then we can mix between noise and noise hover. And then drive between the two using that V hover area. And then let's just see what happens. Okay, it's a bit more bumpy underneath. Let's increase that a bit. Okay, that's crazy, right? Like now let's increase the resolution of this sphere. So it's currently on 16 on detail. Look at that. And then can even go a bit further than that. Let's go up to 64. Whoa, that's like, don't tell me that's not cool. Don't tell me that doesn't look like an impossible piece of thing. All right, that's it. That's like the bulk of the shader work done. I mean, you can happily just log off here, but I'm gonna do a few things to kind of take it to the next level. You can see here that when I kind of unhover, it just stays there. Also, it just like jumps around, like there's no smooth motion. So to smooth that out, we're gonna go back into the React component. So rather than just passing mouse motion directly, we're gonna animate smoothly towards it. And the way that we do that, we need to introduce one more variable. So we need a target. So rather than setting it directly here, we're going to set the target, and then we will then animate towards that target. And then you can play around with that value, see whatever effect you like. We can sort of build on what we currently have. So we can pretend like the mouse position has just moved far away. We're going to say the mouse position, rather than look to the target, which is not set, look at that. It just disappears slowly. That position is going into the center, that's why. So it's kind of like, this disappears. Super cool. There it is. An interactive sphere using perlin noise and custom vertex and fragment shaders.